Hello dear friends, welcome to a lecture of vector calculus. We are studying differential operators, and in that we are studying directional derivative of scalar point function and a vector point function. In our last lecture we have studied directional derivatives of a scalar point function along positive direction of x, y, z axis. If phi is a scalar point function, then the directional derivative of this phi at point A along positive x along coordinate axis, along positive direction of coordinate axis of x, y, z axis are respectively that we have seen dou phi by dou x, dou phi by dou y and dou phi by dou z. So these are the directional derivatives along positive direction of x, y, z axis of this scalar point function. And if you take the negative directions, then this will be negative of dou phi by dou x, negative dou phi by dou y, etc. Similarly, if we have directional derivative of f bar along at a point which is x, y, z along the same positive directions of x, y, z axis, then that will be exactly similar to this dou f bar by dou x, dou f bar by dou y and dou f bar by dou z. So these are the directional derivatives of scalar point function and vector point function along positive directions of x, y, z axis. And if you take the negative directions, then there will be negative sign for these partial derivatives. Now we shall study in this lecture the directional derivative of scalar point function along any line, and similarly the directional derivative of a vector point function along any line. So we shall consider the line as AP. Let AP be a line, be a semi-line, one directional line, semi-line through A. The point A is, we will consider x, y, z, and let LMN be the direction cosines of the line AP. This we will have. We shall draw the figure. Suppose these are the coordinate axes x, y, z, and earlier we have considered line parallel to positive direction of x axis, but here this is any line, so may not be parallel to x axis or any axis. Suppose this is the line, this is the line AP, and now we will suppose the distance be r between A and P. The coordinates of A we have written as x, y, z. Let the distance of P from A be r. If this distance is r, AP distance is r, then we can write the coordinates of P in terms of the DCS, direction cosines of the line r, L, M, N. Therefore, the coordinates of P are and we will write as, we know this from our earlier part of vector geometry. The coordinates of P are, P is the point x plus LR. The coordinates of A are x, y, z, and now we are writing the coordinates of P with this distance AP is r and the DCS of the line are LMN, and therefore x coordinate of P will be x plus L times R. Y coordinate of P will be y plus m times R, and z coordinate will be with reference to this point A, z plus the DCS are L M N N R. So these are the coordinates of P. And now we will form, we have earlier defined the directional derivative of a scalar point function phi at point A is phi p minus phi a divided by AP, and therefore we shall form that. Now phi p minus phi of A divided by AP, limit of this as A tends to P is the directional derivative of phi at point A, and this is now equal to, so what is phi of P? P having these coordinates, so that is phi of x plus LR, y plus MR, z plus NR, minus phi of A, that is phi of x, y, z, and the whole is divided by AP. And what is AP? AP is R. So this is the expression that we will have. So this is equal to phi p is this much, phi a is this value, and divided by AP, AP is R. Now we will suppose this as relation 1. We will see what is the value of the numerator, and that we can obtain by Taylor's theorem of 3 variable, of Taylor's theorem of a function of 3 variable, by Taylor's theorem of a function of 3 variables. Taylor's theorem we have studied in partial differentiation, chapter of partial differentiation, and we shall use it here. Earlier that we have studied Lagrange mean value theorems, Lagrange mean value theorem, etc. Cauchy mean value theorem also we have studied, and Taylor's theorem is a generalization of Lagrange mean value theorem, but the theorem we have studied for is for 1 variable, and here we want to use it for 3 variable. See what is actually the Taylor's theorem. Lagrange theorem is A plus H, another form of Lagrange theorem, that is LMVT is f of A plus H is equal to Fa plus H f dash of A, f dash of A plus theta H, where theta is between 0 and 1. This is the Lagrange mean value theorem. Actually this theorem we are going to use, Taylor's theorem is the generalization of this theorem. And what is the Taylor's theorem? Taylor's theorem is f of x plus h is equal to f of x plus h f dash of x plus h square by 2 factorial f double dash of x and plus h cube by 3 factorial, etc. Now how to use these theorems here? So these are the theorem we have written for single variable, but here this is function of 3 variable x, y and z, and therefore if you write that this result, so phi of x plus LR, y plus MR, z plus NR, this is equal to, now you may see f of A plus H, H is here, and instead of a single variable here there are 3 variables. So how it is written? F of A plus H times f dash of A plus theta H, and therefore here it may be taken as f of x plus H, y plus k, z plus L, and that will be according to this. This is or you may see any one of this, it is of the same form. What is the difference in this? Here it is continued up to infinity, and in approximation we shall neglect the higher power terms of h square, h cube, etc., and we consider only the 2 terms. Now this is the same form. Instead of A here is x. So f of A plus h is f A plus h f dash of A plus theta h. A plus theta h is a point between A and A plus h. So, better to consider the earlier form, and therefore here, so what will be this? This will be f of x, y, z, the first term, f of x, y, z. It is f of A plus h is f of A, and plus, but there are three variables. Here it is single variable, therefore we have written h into f dash. Now here it will be h into that derivative will be with respect to the first variable, or that is h f dash of x. X is the first variable and derivative with respect to x is f dash of x, and therefore that derivative we have to write partial derivative dou f by dou x. This is the notation for partial derivative. It is actually a derivative of f with respect to x at a point A plus theta h, and that point may be written as ABC, plus, and corresponding to this, now that is k, and partial derivative of f with respect to y, that is fy, and same point will be at ABC, and plus L, partial derivative of f with respect to z at some point ABC is a point between x plus h, y plus k, z plus L on the line joining these 2 points. And so this is the Taylor's series form of or approximation form of Taylor's series for plus higher power terms of h, k and L. And our assumption is AP is small, that P will approach towards A, and therefore this R is very small, R will tend to 0, and therefore this LR, MR and NR terms will be very small, and therefore we neglect the higher power terms plus so on. So this is actually the Taylor's theorem for 3 variables. So here it is Lagrange mean value theorem, this is Taylor's theorem, and this is Taylor's theorem for 3 variables. Now this theorem we have to use here, and see what will be this. This is equal to first term is, instead of f there is phi. So phi of x, y, z. So this is Taylor's theorem for 3 variables, and that will be phi of x, y, z plus it is h. What is h here? That is LR plus LR, and partial derivative of phi with respect to x. This is the notation dou phi x suffix x means dou phi by dou x. Partial derivative of phi with respect to x, and we take a point as ABC, plus k. What is k here? That is this y plus k. Here it is y plus mr. So it is mr partial derivative of phi with respect to y at some point ABC, plus next z plus nr. So it is nr partial derivative of phi with respect to z at point ABC. So you please try to understand how we have used the Taylor's theorem for a function, Taylor's theorem for a function of 3 variables. That is there are 3 variables x, y, z. So first it is phi of x, y, z plus this LR into partial derivative of phi with respect to x at some point ABC, and plus MR partial derivative of phi with respect to y, etc., where ABC is a point on the line AP between A and P, that means joining x, y, z and this point. Now so this theorem we have using this Taylor's theorem. So this is for our reference. Now we with the help of this expansion we rewrite equation 1. So from 1 we have what will be phi p minus phi a divided by AP, and this is equal to see the difference of these two. So shift this term on this side, and the difference will be as this LR into phi x MR etc. This will remain, and again that is divided by R. So therefore R cancels from each term, and what remains is L phi x means partial derivative of phi with respect to x at ABC plus m phi y means partial derivative of phi with respect to y at ABC plus, you can easily check this, shift this term on this side and that is the numerator, and divide the rest expression by r. So, r cancels and it remains like this. So, z that is n dou phi by dou z at ABC. So, this is the expression we have obtained. Now, what we want to find the directional derivative means we want to take the limit of this as p tends to a. Now, as p tends to a. Now, what about this point ABC? ABC is a point on the line AP. So, therefore, this will also approach towards A. So, see, this is the line AP. The coordinates of A are x, y, z, and P that we have these coordinates. And ABC is a point here between the line on between A and P on the line. And as this P approaches towards A, ABC will also approach towards x, y, z. The point ABC approaches x, y, z. And therefore, taking the limit as p tends to a, we get so take the limit of this as p tends to a. So, limit p tends to a of phi p minus phi a divided by AP is equal to L phi x. ABC becomes now x, y, z plus m dou phi by dou y at x, y, z, and plus n plus n dou phi by dou z at x, y, z. Or in short, this is the directional derivative. The directional derivative of phi at A along the line with DCS LMN, hence, or thus, directional derivative of phi at point A x, y, z along a line with direction cosines, or in the direction along the line with along a line with direction cosines LMN is this expression, that is L. We can write dou phi by dou x plus m dou phi by dou y plus n dou phi by dou z. So, this result we shall remember. The directional derivative of a scalar point function along phi at a point x, y, z along a line with direction cosines L, M, N is L, the first cosine, L partial derivative of phi with respect to x plus m partial derivative of phi with respect to y, and partial derivative of n into partial derivative of phi with respect to z. So, thus we have obtained the directional derivative of scalar point function. Now, we shall obtain the directional derivative of a vector point function along any line in the same manner, and the result will be exactly the same. So, similar, that means if you have the directional derivative of f bar at point A x, y, z along a line with direction cosines LMN, then the result will be L dou f bar by dou x plus m dou f bar by dou y plus n dou f bar by dou z. That result we shall obtain. The directional derivative of a vector point function along a vector point function, and that function we shall denote by f bar along any line with with the DCS element. So we shall start with the same line, semi-line having DCS element. Let AP be a line through or be a semi-line, one directional line through the point A. That point we will write as XYZ. Coordinates of A are XYZ. Let the DCS of AP, the direction cosines of line AP be LMN, or LMN be the direction cosines of line AP. Now we shall further consider, suppose this expression f of f bar of XYZ is equal to, this is a vector, and we will resolve this vector in terms of XYZ components or along XYZ directions, and that we will assume I is the unit vector along x axis. So I f1 at XYZ plus j f2 at XYZ, expression of a vector in terms of ijk components. So this is a vector, and that can be written as I into f1 plus j into f2 plus k into f3. Three components we have written, and therefore what will be f bar at A? F bar at A will be I f1 at A plus j f2 at A and plus k f3 at A. So this will be the expression. A is the point XYZ. Every vector has components ijk along XYZ axis, and that vector is expressed in this form. Three components that we have written. And similarly, what will be f bar of P? F bar of P will be I f1 at P plus j f2 of P plus k f3 of P, where what about this f1, f2, f3 are scalars, and only the vectors will be I, j, k, where f1, f2, f3 are scalar functions having continuous partial derivative, first order derivative, because that is required to get the directional derivative. The function must possess continuous partial derivative of first order, having continuous or possessing continuous first order partial derivatives with respect to x, y, z. And now we shall form the directional derivative, or to obtain the directional derivative, what we need is f bar p minus f bar a divided by ap. So now, and then its limit. Earlier we have written phi for scalar point function to obtain the directional derivative at a. So we have to take a p as a point on the line, and then we have to consider f bar p minus f bar a, etc. So we have let the direction cosines of line AP be LMN, where p is a point, AP be a line we have written here, AP be a line, semi line through A, and divided by AP. So this is the expression. So we want, and if its limit as p tends to A will be the directional derivative of f bar at A. And what is f bar p? Here we have written f bar p, and what is f bar a is here. So we have to subtract this and divide it by AP. So what will be the subtraction? You see, this subtraction will be component wise. I f1p minus f1a divided by ap. So that is I f1p minus f1 at a divided by ap. So subtraction of I component, then plus j, that is will be f2p. It is f2p minus f2a. We are subtracting f bar a from f bar p. So f2p minus f2 at a divided by ap plus k f3p minus f3 at a divided by ap. You can see this difference of f1 f bar p minus f bar a, and it is divided by ap. Each term is divided by ap. And now we shall take the limit as p tends to a on both sides. So taking limit as p tends to a from both sides. We have to take this limit on both sides, and what we shall get is limit p tends to a f bar p minus f bar a divided by ap is equal to, and on the right side we have to take the limit of this each, and that will be I limit p tends to a f1p minus f1 at a divided by ap, and plus j limit p tends to a f2 of p minus f2 of a divided by ap plus limit plus k is there, plus vector k, and these I, j, k vectors are independent of the limit because these are unit vectors, and therefore we can write it outside the limit. Limit p tends to a f3p minus f3 at a divided by ap. But this is equal to, now what is this f1 is scalar point function, and this will be the directional derivative of scalar point function f1 at a along the line ap, and we have earlier obtained that result. So directional derivative of a scalar point function phi along a line ap is L dou phi by dou x plus m dou phi by dou y plus n dou phi by dou z, and instead of phi here the function scalar function is f1. We have written f1, f2, f3 in this expression are scalar. This is a composition of vector in terms of ijk components, and these are scalars. So therefore this is a scalar point function, directional derivative of scalar point function, and its result is L dou f1 by dou x plus m dou f1 by dou y plus n dou f1 by dou z. That result we shall use here. So that is L, that is I into bracket. So this is the directional derivative of f1, and that is L dou f1 by dou x plus m dou f1 by dou y plus n dou f1 by dou z. So this follows by the earlier result exactly. Instead of phi here it is f1. And what about next term, that is j, plus j, and this f2 is the scalar function. So therefore its directional derivative at the same point a will be L. L, m, n are the direction cosines of the line ap, and therefore that will remain the same. L dou f2 by dou x, function is now f2, plus m dou f2 by dou y and plus n dou f2 by dou z. And next result is plus k. This is the directional derivative of function f3, and that will be L dou f3 by dou x plus m dou f3 by dou y and so on. So thus we have written the using the directional derivative of scalar point function. Using the result of directional derivative of a scalar point function. And next this can be simplified, and that for the expression we shall take L common. You see this addition we shall do, and that we will do vertically. L is common, and then the expression which remains in bracket is, if we take L common from these, then I dou f1 by dou x plus j dou f2 by dou x plus k dou f3 by dou x will remain in bracket. So I j dou f2 by dou x plus k dou f3 by dou x, that will remain in bracket, plus m. Now take the second terms here, and from these second terms we add these second terms, take m common. So if m is common, then in bracket it remains I dou f1 by dou y plus j dou f2 dou f2 by dou y plus k dou f3 by dou y. See, and now take n common, plus n in bracket I dou f1 by dou z plus j dou f2 by dou z and plus k dou f3 by dou z. So these terms will remain in bracket. We have added this. And what is the first expression, L? So this I dou f1 by dou x plus j dou f2 by dou x and plus k dou f3 by dou x is the partial derivative of f bar with respect to x, and that is L dou f bar by dou x. This bracket is dou f bar by dou x. How it is? Because we have written what about f bar, that is I f1 plus j f2 at xyz and plus k f3. So what is the dou f bar by dou x? Dou f bar by dou x will be I dou f1 by dou x plus j dou f2 by dou x plus k dou f3 by dou x, and it is the same. See, therefore this is dou f bar by dou x plus m. What is this expression? This partial derivative of again f bar with respect to y, and that is m dou f bar by dou y plus, and the third term is n partial derivative of f bar with respect to z. So this is the directional derivative of a vector point function f bar at point A along the line having DCS L Mn. The result is exactly similar to that of we have obtained for the scalar point function. For scalar point function, it is L dou phi by dou x plus m dou phi by dou y plus n dou phi by dou z. Instead of phi, here the function is a vector point function f bar. So f bar first we have written in the components of I, j, k, and then where f1, f2, f3 are the scalar functions, and then here we have used the result for the directional derivative of scalar point functions, which we have obtained earlier. So that we have written in bracket, and thus we have obtained the directional derivative of a vector point function. So this is, or we can rewrite the result as thus: the directional derivative of f bar of a vector point function of f bar at A at xyz along a line with direction cosines. I am writing in short, direction cosines Lmn is L dou f bar by dou x plus m dou f bar by dou y and plus n dou f bar by dou z. So thus in this lecture we have obtained directional derivatives of both scalar point function and vector point function along a line having direction cosines element, and the results are similar for scalar point function and for vector point function also. So remaining part we will continue in our next lecture. Thank you for watching the lecture.